I'm Nidia Gallego. I'm going to be talking about, hoping to give you just a quick overview, a taste of the various activities that we're doing at Oak Ridge related to graphite-salt interactions. Primarily, I will give you, the focus of our research is understanding salt intrusion. We're not measuring just the weight change of the samples, but we're more interested in understanding where the salt is going. So the depth of penetration and the salt and how the salt distributes within the graphite sample as a function of pressure, temperature, time, and graphite grade. We also studying and trying to understand the interfacial relationship between the salt and the graphite, understanding wetting behavior of the salt on graphite surfaces. We are also studying the tribological properties of graphite immersed in molten salts, and we're working with the ASTM and the ASME Community to develop standards and to try to qualify graphite for ASME under the ASME code. Before I go, for those of you that are not familiar with graphite, graphite is not a simple material. Graphite is more of a composite. We got a filler, a binder, and a large network of porosity. Most graphite grades are about 20% porosity. And I was actually looking there at approach, let's say graphites, because you may have 20 different graphite grades. They all will come and say, yes, they're 99% carbon with a few hydrogen and oxygen, but all those 20 graphite grades are likely going to be very different when it comes to microscopic behavior and properties. Most of that has to do with the porosity. That porosity is developed during the manufacturing process, and depending on that manufacturing process, you will have pores that are very different when it comes to shape, size, and connectivity. The shape, size, and connectivity of porosity is going to dictate a lot of the behavior of the graphite, from the irradiation behavior to how the graphite behaves with the molten salt. So salt intrusion, at Oak Ridge, we have developed not only the capabilities to do intrusion, so we can expose graphite samples into, right now we're only doing fly nag, to molten fly nag at various conditions of pressure, temperature, and time. Our system is designed to go up to 10 bar and 750, and we can keep it there for longer extended periods of time. We have, again, not only doing the measurements of the weight changes before and after to see how much salt is entrapped in the graphite, but we have demonstrated and implemented the use of neutron imaging to study how that salt distributes into the salt. This is a 3D rendering of a sample exposed to graphite salt. We can subtract the sample before it's exposed to salt, and we can see where the salt is going into that graphite sample. This particular sample in here, if I go here, the particular sample that I just showed, it is about 10 by 20 millimeter, 10 diameter by 20 meter high. So how that salt distribute again is going to be a function of your intrusion conditions, pressure, temperature, and time, and also graphite grades. Not all graphite grades you're going to see that much salt going into it. So we continue to do these experiments, these measurements at various conditions of pressure, temperature, and time, and using a wide range of graphite grades. We have a more recent document, a paper that was published this year, so feel free to look at that. The other factor that is important to trying to understand and potentially model or predict salt intrusion is understanding the wetting behavior. So we have implemented a high temperature optical dilatometer with a software for contact angle measurements. So here we can see how this salt, we start with a solid pellet, we raise the temperature, and we can see how that salt goes from solid to liquid. It shows the non-wetting behavior by a contact angle greater than 90. But as we continue to increase temperature, and if this goes maybe, you will observe that that contact angle changes as the temperature increases. You're also going to see that there may be, one thing what that video progresses, one thing that we're interested in is understanding how the surface properties of that graphite, because again, they're very different, that roughness may be affecting. We're also looking into, you can see how when you start reaching over 700 degrees, it goes from a no wetting to wetting behavior. If you start observing on the size of that big bubble, you're also going to see smaller bubbles coming into it. This is not pressurized. This is atmospheric. There is an argon blanket flowing into it. And you can see some small bubbles kind of popping into it, basically indicating that the salt is going into the pores and coming up into another surface. Surface quite different. This is an HOPG, highly oriented palladitic graphite, very smooth surface, basically basal planes. Graphite, manufactured graphite is a lot rougher surface. We have seen this is basically an indication of those extra amounts of salt that is popping up in other areas. The original salt bubble was in the middle of this one. Quickly, the next area that we're doing is understanding wear behavior of graphite in molten salt. We completed initial scoping studies to understand the friction behavior, to measure the friction coefficient and the wear behavior of graphite sliding in the sliding mode against a 316L flat. That work was published. We used for that work a system that it was at Oak Ridge, not ideal for the system since it was in a glove box, but more recently we have completed the installation of a new glove box and a tribometer that is completely enclosed. So we're hoping to continue these studies in a more controlled environment. Not only going into a pin of graphite over a metal surface on alloy surface, but we're hoping to go into graphite or graphite and possibly mimicking the pebble on pebble movement and friction. Last but not least, we are involved with the ASTM community. We're trying to develop standards or see if there is need to develop standards to understand the effect of salt intrusion in graphite properties. And the ASME code, there are gaps in the code that prevents, graphite to be fully qualified for use in nuclear reactors. So most of the work that we're doing here, the funding that we're getting is based or is geared to trying to address those gaps so that we can complete the qualification, the code qualification of graphite for use in nuclear plants. I don't do this in isolation. I lead the work, but I got a lot of people working with me. So this is the team at ORNL. We work with people outside ORNL too. This is our list of publications. I probably should have mentioned too, we use HIFER and we're getting funding from the MSR campaign and the TRISO and Graphite campaigns. This is the list of publications. They're all available at OSTI. Feel free to reach out to me if you had any questions. I'll be around. Thank you.